It's not even my work yet, right? Like I'm still working on this.
Wow.
Yeah, it's probably not just the first time I'm presenting it. It's also the first time I'm going to be articulating it. So it's going to be all over the place. I hope that's okay. Uh,
Sure.
yeah. Yeah. First of all, thanks, Ablash, for setting this up. Oh, awesome. We have Jeff as well. We have 100% attendance. Hi, Jeff. What's up?
Yeah.
Hey, so yeah, I'll get started, guys. Quick introduction. I'm working on Questbook, and at Questbook, we're trying to build a decentralized university. But the thing of interest in today's discussion is that um, we want to enable people to come and learn and earn in the process, right? So we want people to come and learn about Web3, transition from Web2 to Web3 developers, and earn some cryptocurrency in the process. So one of the problems that we hit was that, hey, all these people who are coming onto our platform are only beginning to learn about Web3. They do not have any experience in Web3. So it was really unfair for us to expect that these people will have any experience in dealing with wallets, in dealing with signing transactions, and stuff like that. And very soon we hit a bottleneck in which, uh, right, like if we do anything on Ethereum or even Polygon or any L2, one of the problems that we face into was people need to have some wallet, some kind of tokens to be able to pay transaction fees, at least, right? The gas fees. And that was an assumption that didn't hold true in the product that we are building, because these were people who were completely new to Web3. They never even installed a wallet. They've never even come across the concept of a wallet. So we stumbled upon this problem in which we were thinking about, hey, how do we still enable people to be involved in the Web3 technologies, be involved in the community, without having to have the prerequisites of the wallet itself, of requiring all these setups. Right. So we started digging deeper, and we thought, hey, one of the most important things we need to enable is a zero gas fee transaction. Right. So having zero gas fees is something that's super super important, because otherwise people would have to have some kind of a token. They would have to have ETH. They would have to have like Matic or whatever token it is. Without that, people just won't be able to transact. So we thought, hey, we need to build a system which has like zero gas fees, like literally zero, not very low, but exactly zero. So that is what we set out to build, and that's what I want to like quickly talk to you about. I'll take a quick pause to see if I'm making sense, if that's the right agenda for this call. Happy to tweak it on the fly as well. Awesome. Thanks. Cool.
So
Yeah.
why can't the new users use a testnet to test out, right? To transact or get used to it instead of having another separate flow?
Hey, yeah, we did experiment with a testnet, but even on a testnet, two, three things, right? Number one, you need to have a wallet. Number two, you still need to have test ethers, if not like real ethers. And most importantly, the third piece is, hey, we're building a real product, right? Like the real product, it's a real currency that we like, a real cryptocurrency that we're dealing with. We have our own ERC20 token, and it's not a toy token. Like it's an actual token that we want to be able to trade on Uniswap, right? So how do we enable that use case is what we've been thinking about. It's not a test kind of an environment. It's more like a prod environment with zero transaction fees. So that's what we really care about.
Got it.
Have you considered stuff like airdrops?
Yeah. Actually, I'm going to be talking about airdrops today. Yeah, so airdrop is an important part of it. However, even with airdrops in the traditional world, you still need to pay gas fees, right? Like even to claim airdrops in a lot of situations, you need to have some kind of a some kind of ETH to like claim the airdrop or something like that. So yeah, even if you like directly airdrop into the wallet, that's also an option. But still, like if you have to transact, you need to pay the gas fees. So that's something that was hugely detrimental to the kind of use case that we had. We wanted people to be able to like quickly send money to each other on the platform, because ours is a platform in which we have micropayments. So we don't want people to be like spending too much gas on very small transactions that they're doing. So all of those put together, it kind of didn't make sense even for us to do an airdrop. So that's why one of the things that was a non-negotiable on our engineering team was, hey, the transaction fees has to be like absolute zero. Otherwise, it's just not possible. We wanted to have like a great user experience. Does that answer your question, Dragos?
Makes sense. Yeah.
Awesome. So with that, any other question? So I just saw Kevin and Halim just joined in. But
Hey, sorry, what's the topic right now?
okay, so the title of the talk is if you're serious about building a dApp, you should build your own blockchain. So that's what the topic is. I'm going to be basically talking about how we can build dApps by building an L2 solution and have like a great user experience, like not compromise on the user experience and still build a dApp. So that's largely the problem statement that I've been trying to build over the last few months, and that's what I want to like quickly talk to you about as well.
Are we going to? I'm going to talk technically about how L2, technically working. Is it possible to mention, like for example, one of the things that I'm trying to understand, like in the last few days I spent on the Arbitrum Discord, and I'm trying to understand a simple flow, like what happened when a user submit a transaction until the end of the cycle after 7 days, like what happened, and like very very hard to understand. Like
Yeah.
I thought that there would be like a chart flow that will be very simple to understand, but no. So this is something that I would love to understand if it's possible.
That's actually exactly what we are going to dive into. I'm going to talk to you about the mechanism design that we have on our system, which is exactly an L2 plasma construction, and I'll explain to you end to end how we are building it.
Great, thank you.
Awesome. So I'll just quickly share my screen. I'm going to be doing some whiteboard. Like I wanted to create a presentation, but yeah, I didn't have time for it. 1 second. Can you all see my screen?
Yeah.
Awesome. I'll just turn off my video because now I'm going to like point the camera upwards because I'm going to be drawing on my screen.
Sure.
Yeah. So yeah, the first thing that I want to talk about is what is called the trilemma in the blockchain space, right? So something that Vitalik talks a lot about. So there are three attributes in a blockchain that is possible. So the first is the decentralization itself. Then there is security, and then there is speed. I would also call it like cost efficiency. So these are like three things that a blockchain could achieve. And what the trilemma states is that you can pick only two out of these. Like you can have either decentralized and security and not speed, or you could have security and speed but not decentralization and stuff like that, right? So what Ethereum largely goes for is these two, right? It's completely decentralized, like super almost ideally decentralized. It has strong security, but it is not particularly fast and it's not particularly cost effective, right? Like the efficiency of cost is pretty low in the sense that the gas fees and all that stuff is very, very high. So what this means is having a lack of speed and cost efficiency is what we were just talking about. That is it really makes consumer facing apps really hard to build, right? So especially when we're coming from the web 2 kind of an experience where everything is seamless and it just works out of the box, and when we come to the web 3 world, the decentralized world, you have to install all of these wallets and you have to have some transaction fees, Ethereum in your wallet and stuff like that, which makes onboarding really, really hard. So one of the things that I wanted in my product is, hey, the speed and cost efficiency are like non-negotiable. So I need this And of course, we need security. What security means is, like if you have money on this system, on this blockchain, how can you make sure that you never lose it as a user? Did somebody message? Yeah, I'm not looking at the screen, so if you have a question, you can just like stop me and ask. Yeah. So yeah, these are the two things that I want to gun for. Like, I want to make sure people who put in money into my system are rested assured that their money is safe. So I want security, and I want to make sure that all the transactions are fast, they're cost efficient, and these are the two things that I want to pick at the cost of decentralization. So this kind of tells us that, hey, you're building a system that's centralized in nature, right? So you're basically just setting up a Web2 service if you're picking security and cost efficiency and letting go of decentralization. I think this is where the concept of an L2 comes in. So what we're going to do in today's session is going to build on top of Ethereum. So we have Ethereum's decentralization and security. We are going to augment that with speed and security of our system. So it's basically an L2, right? So this is giving you decentralization plus security, and we are going to go for speed plus security. So that way we have like a nice complementary kind of a system. And what we are going to be looking at today is called Plasma. It's one of the more simpler constructions for an L2 system, and I'll walk you through how we've implemented Plasma. So there are multiple ways to implement Plasma. What I'm going to talk about today in particular is called the MVP, which is minimal viable plasma, that Vitalik presented, I think, in 2017, 2018. I'm going to be like going over a lot of abstractions here at the cost of technical correctness, but happy to dive into the technical details also like later in this call, or probably on a different call as well. So with that, I'll quickly start talking about the construction itself, right? Like, how will this technology work in which we have all the decentralization benefits of Ethereum, all the security that Ethereum provides, and yet have like a fast transaction system in which we can like modify it to the requirements of our particular application that we're designing. Right, so what we're going to do is we're going to have the base layer of Ethereum, and we'll have a separate, completely centralized server, right? So these are going to be like two independent systems. And what this server is basically going to do is it's going to hold two databases. Very simple. The first database is of the transactions, and the other is the blocks. Right, so we're going to be building a blockchain on top of Ethereum, or an L2 kind of a blockchain. The transactions are simple, like it'll be like a from, to, value, some metadata, and a signature of the entire thing, right? Like the signature from the sender. And the block will really just have all the basics, that is like the block number and the previous block. A bunch of other headers as well, which we'll get into later if need be. Right, so the only thing I want to call out over here is that the transactions are stored as UTXOs. Are you like broadly aware of UTXOs? Like, do you want me to like quickly talk about UTXOs? Anybody?
Maybe like one sentence. I am familiar. Just like want to make sure that.
Sure. So UTXO stands for Unspent Transaction Output. So what that means is, hey, instead of storing the, okay, so sorry, I'll take a step back. Let's say you have 10, so Alice has 10 coins, right? And she wants to send 8 coins to Bob. So what she would do is create a transaction in which she would send 2 coins to Alice and 8 coins to Bob. Right, so the 10 is now broken into 2 plus 8. So basically what this means is now this output is now used. Now I cannot use this for another transaction. Like I cannot do one more transaction to say Carol and Alice, right? So once this has been used, it gets broken into 8 to Alice and 2 to Alice and 8 to Bob. And now Alice can like spend these again. Like she can do like 1 to Carol and 1 to Alice. If she wants to send 1 to Carol. So what that means is now this output. So this is the output from this transaction, in which like the input is 10 from Alice, 10 coins of Alice, and the output is 2 coins to Alice and 8 coins to Bob. So each transaction output can be used exactly once, right? So once you've used this transaction to send it to Carol and Alice, you cannot use this transaction again. If you want to make another transaction, you have to make it from here, right? So that this is basically UDXOs, right? So whatever is unspent. So at this juncture, these are the 3 outputs that have not yet been spent, right? So any new transaction that's going to happen on the platform is going to be one of these 3. Does that make sense? I glossed over a lot of details. Got it. So
it's like how Bitcoin works.
Yeah. Bitcoin works on UDXO, correct. Ethereum does not. So basically, so we'll be storing all the transaction in the form of UDXOs. However, that's a minor detail. So basically, these are the entries that get put onto the database, right? So how does money enter the system? And so for that, what happens is not only do you have a server, but you also have a smart contract on Ethereum's main chain, right? And if anybody wants to start transacting money on this server for 0 gas fees, the first thing that they need to do is deposit, right? So let's say we are going to operate in a cryptocurrency, some ERC20 token. So let's say YCC, right? Let's say we have YC coins. So if I want to transact in YC coins, first I'll come deposit 10 YC coins into the smart contract, right? So as soon as somebody deposits 10 coins into the contract, an event get triggered, saying that, hey, a new transaction has been made into the smart contract, and the server will make one entry. That entry will say 0x, meaning that this is a transaction that is new. It's not an existing transaction. A new transaction has been created from thin air to, let's say, Alice was the person depositing it, to Alice, and the number of coins is 10. Right, so one entry gets added whenever somebody deposits money into this contract. Right, so the same way, let's say Bob does it as well. Bob deposited 5 YCC here. So the database gets updated. And now let's say there is one app in which you can send money, right? So there is a send money option on your app, and that interacts directly with your server, and the server can can keep updating this database, saying, hey, now there's a new transaction from Alice to Bob for 2 coins, right? And then there's some Bob to Carol for 1 coin, and so on, right? And all of these are like really cheap. All of this is just a database update, so this can be done free of cost. It does not cost the server anything at all, so it'll just keep updating it, no gas fees, and they'll be able to transact, right? And every 1 hour, or let's say every 24 hours, or some arbitrary time, the server will submit what is called a Merkel proof, like a Merkel root. saying, hey, these are the 100 transactions that happened in the last 24 hours. And here is the root of all of those transactions. Are we aware of what a Merkel root is? Do I need to quickly touch upon that? Okay. Yeah. Does anybody want me to talk about a Merkel root?
Can you just explain the basics like that?
Sure. So a Merkel root is, let's say, there are 4 transactions in your system. So you create a tree like this in which all the transactions are leaves, right? And each node in the tree, except the leaf nodes, is nothing but a hash of its children. So this is like the hash of T1 and T2 will be stored in this block. This block is hash of T3 and T4. And this is going, and let's say this is called A, this is called B. This one is going to be hash of A comma B. Right, so this is called a Merkel tree, and
Okay.
This hash that is on the root node is called the Merkel root.
Got it.
Right, so this has actually 2 properties, which is important, right? So one is, let's say you make an edit, you make a change in one of the transactions. The Merkel root changes because once you make an edit over here, this changes, and because this changes, this will also change. So the entire branch will change whenever you make an edit into any one of these transactions on the leaf node. That's property number
Got it.
1. Property number 2 is, if there is an update that happens on any one of the leaves, this branch does get updated, but does not affect any branch that is not touched by this. Okay, so there's no update that happens in this part of the branch because of a change over here. So these are 2 basic properties of a Merkel tree that we need to know at this point.
Got it. Yeah, just one last question. So,
Yeah.
Does that mean the depth of the tree is always 3?
No, so what typically happens is you would set something like, let's say, 2 power 10, right? So these are the maximum number of transactions that can happen in a particular block if you define that. So your depth will be 10. So depending on how many transactions you want to support in a block, you would set the depth of this particular tree.
Makes sense.
Yeah, so in this case, since so we will say that our block is going to hold only, let's say, 4 transactions. So we'll say it's going to be a tree of depth 2, right? So every 1 hour a block gets created, basically a set of all these transactions that are in the database. You convert them into a tree, and then you calculate the Merkel root. Right, so the Merkel root is what gets deposited into the smart contract every, let's say, 1 day or every 1 hour, something like that, arbitrarily. So this is basically proof that says, hey, this is the state of the block at block number, let's say, 10. Right, so at block 10, these are the transactions that have happened. So we will see why it is important to store a Merkel root over here. So this is great, right? You're able to do all of these transactions absolutely free of cost. But what if the owner of this server decides, hey, I'm going to just create 0x to Alice. I'm going to mint 1 million tokens without Alice making any deposit over here, right? So the server can add one more entry over here, without anybody asking a question. So what do we do? This seems like a possible attack, right? So what is expected from the participants in this ecosystem is, whenever a malicious entry gets made, you just exit the system, right? So you say that, hey, this server is not acting honestly anymore. I want to leave. Just give my money back. right? So if you detect that something wrong is happening and you want to protect your money, you come and say, I want to start an exit. Because if you remember, one of the things that we kind of are gunning for is speed and security, right? So we want to make sure that if anybody deposits money into our server, it's always available, right? Hey, just give me one moment, please. One moment. Hey, sorry, I had another call. I just pushed that by a few minutes. Yeah, sorry, I was saying, hey, if anybody wants to exit, we want to make sure that their money is always safe, right? So for that, we have a process called start and exit, right? So what you would do is you'll make the following claims that, hey, at block number 10, my balance was 25 coins, right? And let's say the current block right now is 15, right? And from 10 to 15, I have not spent any money, not spent these 25 YCC, any of this 25 YCCs, basically saying that between 10 to 15th block, I did not make any transaction. My last transaction was in block 10. Right, and lastly, you would present a proof that my balance on block 10 was actually 25 YCC. And you do this by submitting a Merkel proof. A Merkel proof is basically the entire branch. So you would say, hey, here's my transaction, my unspent output, and this is the parent, this is the parent, and this is the root, right? So that is what forms a Merkel proof, right? So the transaction itself, the first hash, the second hash, all the way till the root hash, right? So if it's a tree of depth 10, you would have like 10 elements here, right? So it's a nice way to represent a proof that, hey, this is the branch in which my transaction existed, and here's the proof that my transaction actually existed in the tree. So the smart contract can look at this proof and say that, hey, yes, in fact, since this person has been able to produce the root, and it actually matches with the root that I have corresponding to the block number 10, this person is probably telling the truth that yeah, they actually had the balance on block number 10. So this is verifiable by the blockchain, by the smart contract, right? The second thing is they can also verify that the balance was actually 25, because they can just look at the value inside the proof that was submitted. So this is also verifiable. What is not verifiable is the fact that I have not spent this money between block 10 to block 15, right? So you can prove that you had that much money in block 10, but you cannot prove the absence of a transaction between block 10 to block 15, right? So that's it's just not possible to create a proof for that. So that is where one more game comes into play. That is called a challenge. So basically what happens is, as soon as somebody starts an exit, their money is frozen. Their money is frozen for, let's say, 7 days. So this is what you were referring to a little earlier, I guess. So for 7 days, your money is frozen. You cannot transact on it. And what is called, depending on the chain that you are more familiar with, you might have heard of the term freeze time or cool down time, or whatever. There are multiple names for it. So basically, for 7 days, the essence is your money is frozen, and in these 7 days, anybody can come and raise what is called a challenge. So this is where the decentralization part comes in, right? So this is where we are going to inherit the decentralization aspect of Ethereum. That is, anybody on Ethereum can verify that so all of this information is public, right? So from the server, all the information of all the transactions that the server is recording is publicly broadcasted. So anybody can come and say for the next 7 days that, hey, wait a minute, this user Alice has actually made a transaction in block number 13 from, let's say, Alice to Bob for 2 coins, and now her balance is 23 YCC. So the exit that she is trying to make of 25 YCC is actually incorrect, and the challenger can also can produce a proof for this, saying that the Merkel root exists. So they would produce this Merkel proof that a transaction was made from Alice to Bob in block number 13, and if this is true, like this is something that the smart contract can again verify, then hey, indeed, this person had claimed that they have not made any transaction after block 10, but here's a proof that they have actually made a transaction in block 13. So this is an invalid claim, and this is kind of rejected. So you can have whatever mechanism you want to, like, punish this particular person for making a false exit. So with all of this, I was hoping this would look a little neater, but this is the mechanism for making sure that your money is always safe in a very centralized setting. So this database itself that we are updating regularly is very, very centralized in nature, but yet we are able to protect the security, and we are able to bring in the decentralized benefits in the system. With that, I'll just take a quick pause before I dive into what this means for all of us, just to see if I'm making sense on the construction itself.
I have a question.
Yeah.
Maybe you're going to talk about it later, but here we have like an example of simple transactions, just like money transactions. What happens if the transaction is actually like calling a function of the smart contract on the system?
Yeah. So. Great question.
So I mean. Yeah. So I mean, my opinion that I'm trying to understand, like in other L2 solutions, I mean, the data, the parameters of the function that this transaction is executing, where are those parameters are being saved? Because, for example, I can send a 10 kilobyte string on Ethereum to save in the storage. 10K is going to cost a lot of money.
Mm-hmm.
So this is what I'm trying to understand.
Yeah. So over here in the database, what we have is a transaction from Alice to Bob and whatever, right? So instead of just having these transactions, you can have function calls, and you can have deployment content, whatever. You can have like different kind of transactions over here, depending on your use case. However, the only thing that matters is 2 things. One, are you able to create a tree out of this and produce a Merkel root that you can deposit into the smart contract? That's number 1. Number 2 is, are you able to create a validation whenever a proof is submitted? So whenever a proof is submitted for a particular UTXO on the smart contract during an exit, you produce a Merkel proof, right? So are you able to construct this proof saying that, hey, this is where the transaction is, This is the parent hash. This is the parent hash. This is the parent hash. This is the root hash. Are you able to create a proof like this that is verifiable on Solidity? If you're able to do that, you can have literally any kind of transaction over here. So
Yeah, but that means that someone needs to read your database and construct out of it the Merkel tree. I mean, but maybe this is your system like a little bit different from Arbitrum, for example. But there, the transaction raw data is saved on L1.
correct.
And
Yeah. So what I have presented to you is called a plasma, in which all the data is stored directly on L2. The data is not stored on L1 at all. However, there is an optimization that we can make, in which instead of storing Merkel roots, we store what is called a ZK rollup. So by virtue of storing the ZK rollup on the main chain instead of just the Merkel root, you can actually store the data itself in a very, very condensed form. But this is something that would demand a longer session in itself. Happy to do one more on ZK rollups. Very, very interesting. So what you're mentioning, I'm sorry, I didn't follow who asked the question, but yeah, that's a great question. So Plasma was like V1 and ZK rollups are like V2, was the more advanced form. Definitely better in the sense that the data is directly stored on L1 layer. So it does come with its own advantages.
But yeah. So thank you. Now I like better understand the difference. So that means that on Plasma you have to have access to the L2 database in order to and you're just using the L1 to verify the data is correct on the L2.
Correct.
Right. I mean you don't. So I mean, what is the L1 security used for? Just for a database that cannot be changed?
Yeah, so L1 is used only to make sure that when somebody wants to exit, honestly, they will always be able to withdraw the money that they have deposited. Let's say you deposit some money and then the server begins to like misbehave maliciously, you will still be able to take 25 coins back out without being affected. So your money is always safe the moment it gets put onto the smart contract. That's the security that we are trying to aim for.
All right. Okay, I think I understand. Thank you.
Awesome. Thanks. That's a great question. So yeah. Sorry.
Quick question. What happens if the centralized server goes down?
So yeah, what will happen if the centralized server goes down? So I'll also introduce one more concept over here that is called watchdogs. I think they're called. Whatever. So some watchtowers, whatever. So basically, which are always listening to the last broadcasted block, right? So let's say this server goes down. You know what was the last block that was published, right? So everybody will start an exit saying that, hey, in this last block that was published, that is block number, let's say 15, this was my balance. I want that money back. And all of them will like just start an exit using block 15 as their reference. Does that make sense?
Got it.
Yeah.
And another quick question: is there any open source framework or something for building such an architecture, or what other technologies would you use for doing that?
Yeah, I have been playing around, but I've not yet come across a simple enough use case that is enabled using this. I think we'll try to open source what we are building, but I've not come across something that is both robust and simple to use. Not yet, honestly.
Cool, thanks. And one quick last question: is this the same architecture Axis is using?
Axie is not using exactly this. This is what Polygon uses.
Okay.
So, however, like just for the sake of technical correctness, is what we are using is a server. So we will call this proof of authority. So what you could also do is, instead of just having one server over here, you could have like multiple servers and they participate in a consensus mechanism. So you could have like a proof of stake over here, you could have proof of work over here, and so on. So yeah, I think what Polygon is using is proof of stake Plasma. So this entire construct is what Plasma uses. Sorry, Polygon uses.
So who is responsible for raising challenges? And I assume they will get rewarded for raising challenges, etc.
Yeah. So one of the there are actually two things. That's a great question. Whenever you are starting an exit, you also put in what is called the challenger fee. Because whenever somebody is challenging, you need to pay the gas fee for the challenge, right? And that's an on-chain transaction. So the person who is starting the exit will kind of pay for the challenger, such that when the challenger succeeds in the challenge, let's say this challenge was actually valid, they get the challenger fee. So this is kind of like putting a stake, saying that I'm speaking the truth. So you can put a stake along with every exit that you start, and this becomes the reward for the challenger.
Okay. And like, can we also participate in raising challenges, or is that tool, or like how do we do that?
Yeah. So this is completely decentralized, right? Like you can listen to events of start exit that is being called. Of course, I've not tried this myself, but I'm pretty sure that this would emit an event, and you can listen to that event and submit one more challenge. This is definitely doable on Polygon.
Got it. Thanks.
I'm curious if you know how Polygon was hacked, if it has something to do with this technology.
Actually, I have not gotten into the depths of what that particular hack was, to be really honest. I don't want to cook up something here. Yeah.
No problem.
Cool. Do we have any other questions? Cool. So awesome. Sorry, Radham, you have something to say?
Yeah, I know. I just like I would love to schedule another call to discuss some more about ZK rollups or optimistic rollups and learn a little bit about that.
Surely. Happy to do it. We can also schedule one more call, because I just glossed over most of the details in this particular call. Like I'm getting physical pain of the kind of abstractions that I've made in this conversation, just to keep it simple. There are of course a lot more technical details.
But thank you so much, man. This was like like really insightful. At least like to get the basics down, and then definitely we look forward to having a more detailed conversation about it.
Awesome. I'm glad you found this of any use.
Thank you.
Cool. Thanks, folks. We'll schedule one more call. This was super fun. Thank you so much. Yo.
Thank you.
Thanks,
Bye.
Yeah, bye.
Bye.